Okay, welcome back to our Lunch with Larry series here at Fox Solution. I just really appreciate you coming again. This is our fifth of 5 sessions, the last one related to design ideation, and we're going to talk today about systems model or model-based systems engineering and how functional models map into the requirement set when we do our development activities. So that's today's topic. Appreciate you coming. Again, this is my contact information. I just wanted to lay it up here so you have the ability to send the webinar registration to other folks that you might think were interested, or LinkedIn accounts, email addresses, and also a link to my Lunch with Larry's YouTube channel. So please feel free to subscribe and get on the list for future informational videos on doing design and how design is integrated into these scalable systems. So thanks for coming. Okay, so again, when we talk about design ideation, the core data model is requirements. And when we build out that set of requirements, what we want to do is have different perspectives to assure that the requirement set is complete. And so one of the things we want to talk about is sort of the order of methodology. And when we do this system, the core set of data is requirements. So that's really the first thing in view. If you don't have a system in place to do requirements management, we want to get that done right away, because everything else that we talk about are a reflection of the requirements or a way to evaluate the requirements to see if those requirements are complete. So first thing is requirements. Second thing we talked about was verification and validation. So how do we develop test evidence to assure that we have the evidence to show that our requirements have been met? The next one was risk management. How do we get this negative view of the design to assure bad things don't happen to people? What do we need to have in the design to assure things don't happen? And fourth was standards management. How do we map in these external standards into our requirement set? And today, finally, we're talking about systems modeling. So this is really how do we model functions and map them into the requirements in a way to assure that what we want to happen with the design, the positive view of the design, the requirements are in place to assure that the design does what we want it to do. Okay, so that's today. So we're just going to start off with a conversation about, what is a function? And when we do systems modeling, what are we really trying to do? What we're trying to do is create a graphical representation of the complex function of a device or of a design. And in order to do that, we have to define the functions and then define these inflows to the functions. And the function ends up being a transformation of those inflows to produce the outflows. So this black box modeling, essentially, we're going to say, what is the function? And then we're going to define the inflows. What are the things that are needed for the function to do the transformation? And then what is the result of that transformation? Once we do understand the outflows, then it's easy for us to write requirements against those outflows as a characterization of the content of the outflow. So it's easy for us to test, does that function perform the transformation as we expected it to? So I'm just going to give you an example and talk a little bit about what exactly are functions. And in this case, what we have is a noun-verb combination. So give you a couple examples. Maybe it delivers vacuum, it gets a configuration, it sets a digital pressure level. So we want a verb and a noun combined together to explain what this transformation does. In this case, in this example that we're going to talk about, it's going to be regulates pressure. And you might imagine if we bought a pressure pump, we could just say the function of the pressure pump as one component of the system is to regulate pressure and then to characterize that outflow. So in that case, we'd have an inflow that might be 120 psi line pressure, and we might have an inflow that's a 8-bit control level to determine or to set what the pressure level is going to be. An outflow then might be 40 psi plus or minus 1 psi. That's what the spec gives us for when we purchase this pump, and it's going to give us 5 CFM. So when we write the requirement, it would read something like the pressure regulator will perform an output of 40 plus or minus 1 psi air pressure at a minimum of 5 CFM. So that's something we can test based on the inflows of control and the inflows of line pressure. And that's what we would get out of it. Now, one of the things you're going to find is when you do this kind of an activity, you might establish a risk. And that risk might be something like, if we get a pressure, an overpressure of 0.75 psi, we end up with a risk. And what we want to do then is create a function, essentially that's a closed loop process control. In that case, we might want to blow this function out into a subsystem. So one of the important things for us to talk about is what is the difference between a system level requirement and a design level requirement. Now, because this function is deployed in one component of the system, It's a design level requirement by definition because we only have one function as it's deployed in one component of the system. But then what we might want to do, as I was saying, is blow this subsystem out into a subsystem. So this regulating of pressure now becomes something that's closed loop control. So we have a proportional valve, maybe a pump, printed circuit board, a pressure sensor, maybe some other components. But essentially what happens now is we have 4 components of the system and functions that are located in each one of those. And when we do that, of course, we still have this verb noun combination. It delivers vacuum or whatever. In this case, of course, regulates pressure. And it defines delivery of a group of functions delivered in more than one component of the system. The chain defined by inclusion of the functions in a group. So the chain is defined by functions in a group. So you can see these red arrows. What we're doing is we're defining how those functions are interrelated with each other. And then what is the outflow of the combination of those functions, not just one function. So again, it transfers inflows into outflows, but now it's at the system level. So again, we have the 120 plus or minus 20 psi air inflow from line pressure, and maybe an integer defines that desired pressure. But now we have an outflow of maybe plus or minus 0.5 psi that's a better control because now we're operating under this closed loop process control. So in this case, when we define multiple functions across multiple components of the system, the outflow is no longer a design requirement. Now it's a system requirement because it's related to functional chain rather than an individual function. And I think you're going to find this concept of functional chains to be very valuable when you're defining how a device functions, because a lot of the review across the systems modeling is going to be, what are these functional chains? How are they related to one another? How are the users of the system related to delivery of this functional chain? These are very important topics so that you understand exactly what the design is supposed to do. All right, so this outflow then, of course, is related to the functional chain, right? Okay, what is a product capability? And this is from a functional modeling standpoint, we have this hierarchy of capability to functional chains. So the functional chains define the capability and the functions define the functional chains. This is really what the design does at a high level, defined by more than one functional chain. When we have that hierarchy, capability to functional chains and functions, the question then becomes, how do we map that to the requirements? And this is just another view of the same thing I just said. We're trying to establish the direct traceability between the functional modeling and the requirement set so that we understand how those two things are related to one another. In this case, the capability is related directly to the user need or user requirement. Different people use different terms. The functional chains are related to the system requirements. And then the individual functions that comprise the functional chains are related to the design requirements. And one of the important things to think about here is those functions, because they're deployed in one component of the system, it's easy for us to say, what design discipline is this related to? So if the function's deployed in software, it's a software requirement. If it's a function that's delivered in a user, it's probably a requirement related to usability. So we want to understand that one of the things that's really nice about this is it helps us to separate what is the definition of a design requirement from a system requirement. And that is something that I think people really get confused about. So it's a nice way for us to understand how are we going to develop our set of requirements and what are they related to. It makes the writing of the requirements much easier. Okay, so the Arcadia method is the one that we use a lot, and essentially what this allows us to do is break the design into graphical levels. So the top level is this operational analysis, and what the operational analysis does is looks at the design space as a whole. What do we need to accomplish in this design space? So we don't have even a concept of what is our design yet. We're just saying we have users, we have an environment that the users are operating inside, and we want to accomplish something. What is that something? What are the capabilities we need to deliver so that the user would get out of the system what they desire? The second level is this functional, non-functional need, which is the system level. And in that level, what we do is we break out the system from the rest of the design space so we know what we're designing and how it relates to the overall design space. Third level is the logical architecture, and that's where we get to this place where we're trying to understand how is it we're going to logically deliver this system that we've defined in the second level. And finally, we get to the physical architecture. And what that does is break out physically what we're going to build into the design and how it's related to these different functions and how the functions are related to one another so that we can define what those requirements are at the physical architecture level. So there's sort of this 4-level breakdown. Now I'm going to talk through one of these examples, so that you can kind of get a better sense of what that really means and how it looks inside of, at least in the Capella tool that uses this Arcadia method. So here we have a capability diagram. And what we're doing here is as I said, we're just opening up the design space and saying, what is it exactly that a user would need? And this example is going to be built around a ventilator. And the reason for that is it's a good electromechanical example. We have users, we have electrical systems, software systems, mechanical systems, disposables, and a piece of hardware. So there's a lot of different aspects to the design. It makes for a pretty good example. So in this case, we're looking at the overall space. We have patient support givers, we have the hospital system, we have a ventilator manufacturer. And what we're trying to do here is just say, if I were going to ventilate a patient, what would I need to do? I need to connect to the patient. I need to establish an operating mode. I'd need to monitor the operational status. I'd like to deliver ventilation. So all these things are just things that would need to be done regardless of what the design looks like and the scope of the design that we're trying to deliver. So in this case, we're going to take this deliver ventilation capability and we're going to expand on it in the operational mode. So what this is then, that deliver ventilation is going to require a bunch of capabilities that are related to it to be able to deliver it. And we have to understand also how is it related to the different users in the system. So in this case, we have this patient assist control mode, we have constant pressure airway. So different things that need to be done to deliver that ventilation. So we get a better sense of it and we define all the capabilities that we're going to have to deliver with these functional chains as we go forward. That's the deliver ventilation again. Okay, so now what we're going to do is we're going to take those and we're going to build out a set of activities. And you can see that this deliver ventilation functional chain is the purple functional chain. And if you go to the left, what you're going to find is the set of activities that we believe need to be delivered to actually deliver ventilation to a patient without any consideration to what we're going to design yet. So we're going to have to connect to the patient. We're going to have to deliver the ventilation. We're going to have to convert the ventilator air to blood oxygen. We're going to have to measure patient vitals. Right? There's a bunch of things that we need to do that we need to expand on to understand better what is needed for this design to deliver that ventilation capability. Okay, so now what we're going to do is we're going to expand on this. And I think what we're going to want to understand then is how to break out the ventilator as a design from the rest of the design space. So now what we're saying is literally what's in the box, what's out of the box. We're going to develop what's called a ventilator, right, quote unquote. And we want to understand what functions, as those activities are converted into functions, what functions are we going to deliver in the ventilator and what are the functions we're going to have outside the ventilator. And I think this is a really important concept because just as an example, if we're going to monitor the patient's vitals, okay, that is going to be done in this blue line as a functional chain delivered by the clinician in the room. So what we have here is this functional chain that starts with monitor patient vitals. Well, what if we wanted to do, pulse oximetry inside the box? So in other words, we wanted to connect pulse oximetry to the design that we're going to be having. Well, in that case, we would put pulse oximetry inside the ventilator, and then we'd show from a software and a hardware standpoint how we're delivering it. What's the algorithm we're going to use? How is that algorithm going to use the data that we're bringing into the box? But in this case, we're making a design decision and we're saying we're going to keep it outside of the box. It's not going to be part of the delivery of the device or the design that we're going to provide. So this is really an important part of it because we're defining from a marketing standpoint, what does this design need to do? And what is it by definition not going to do? And of course, if you can imagine, the usability analysis is going to be different if the clinician is delivering the vital monitoring. That's going to be a different risk. It's going to be something different that we need to deliver than if we delivered it in the box. The risks are going to be entirely different. So we really need to know physically how we're going to deliver this design to better understand how we're going to analyze the risk. So that we'll get to that in a minute. But very important step here is to say, what's in the box, what's out of the box. So again, we have this deliver AC mode, and the deliver AC mode is one of the capabilities that's related to deliver ventilation. So we're breaking it down further and we're saying, okay, this is a component of how we're going to actually deliver that functional chain. And of course, we have the start and stop ventilation at the front of the green line, which is the functional chain that's delivered at this system architecture level. Okay, so now we have the logical functional, and we're dealing with this capability that's part of the deliver ventilation line. And so we have deliver AC mode that's been broken out into the logical deconstruction. And you can see here that now we have the functions, but there's many more functions. And we're defining where those functions live logically inside the system. So we have a ventilation system, as we had in the last diagram. But now we're going to say, okay, we're going to need an exhalation valve. We're going to need an O2 valve. We're going to need an air generator. We're going to need a user interface. We haven't physically said how this thing is going to be done, but there are components, logical components of this system that we're going to want to have in place. So this helps get us prepped up to understand when we get into the physical representation of the design, what is exactly going to be part of that? Are we going to need to develop a user interface, and is the user interface going to be a touch screen or is it going to be buttons? Not sure, but we know we need to interface with the user in this way because we have functions that the user is delivering that it needs to interface with the design. So that's a much more detailed view, and it gets us ready to okay, now we're at the point where we can really start talking about making a physical design. And again, it's deliver AC mode. Same thing as before, except now with more detail and the logical components defined. Okay, so now we're finally down at this physical level. Now you look at this diagram, it's a little bit of an eye chart, but you can see how much detail is now developed. Not only do we have the components of the system, now we have the physical representation of what those look like. So if you look at the top here, we have the ventilator, right? But the ventilator is now a component of the ventilator is the CPU printed circuit board. Inside or deployed inside the printed circuit board, we have ventilator software. The ventilator software has a module called breath delivery or display status or prompt for settings. These are different modules of software inside of that ventilator software module. And now what we start to see is the physical connection between each one of these software components. And not only that, but when we start talking about taking one of these functional chains and decomposing it, we're going across multiple components of the system and multiple disciplines by definition. So we're not only discussing how we're going to deliver it with the turbine at the bottom here, but we're also talking about what is the role of this patient support givers? How are they interfacing with the display and buttons, which is then interfaced with the LCD panel that is part of the CPU, and then the software that's related to it. So we're going across multiple components to deliver this exhalation functional chain. Very important because now we're also saying physically, what is that connection? Is it a Bluetooth connection? Is it related to, a Ethernet connection? Exactly physically, how are we going to be connecting these things together? Very important aspect of it. So that's the system's requirement. That's the system requirement is going to be related to that functional chain. And then, of course, the design requirement is going to be related to the outflow of an individual function as it's transforming that inflow. What is the characterization of the outflow of that function, that individual function? So this kind of starts to help you understand there is an enormous difference between the system requirements and the design requirements. And we need to get to the place, as we talked about last week, in the design requirements where we understand which discipline is the design requirement related to so that we can do the risk analysis with the format of the FMEA that's appropriate for that discipline. And so software FMEAs are different than hardware, which are different than usability, for example. So we really need to get this broken down so that we understand where that function's deployed so we can identify what discipline it's related to so we can do our risk management work. Once we get to this point now, we can also start to assign the functions to the engineering staff that's going to be delivering that aspect of the system. So really nice now, I can give the software people a functional breakdown with the physical connection of the components so that we understand what does this module of software need to deliver. And not only that, but physically what is it connected to in the hardware system so that they can do their job and actually deliver what it is that they want to deliver. So very important. So in this case, I think we kind of have a clearer understanding of this physical model. Now, when we go to the requirements set, what is it that we're looking at? Well, the requirements then have a function. As we said before, the function maybe is generate airflow. If generate airflow is in one component of the system, then the design requirement would be related to the function that's delivered, the outflow of the function that's delivered by that function. So that is the connection point between the requirements and the functional modeling. It's very important. And the nice thing about this is if you want to start understanding then what is exactly going to be our end game here, how many requirements do we need to write? And I think that's one of the things that's really difficult in a design. When am I done? How do I know that I've written all of the requirements? This is something that I've really struggled with in design. You know, somebody will say, I need you to write the requirements for a subsystem. And, you know, the tendency is to just write all the requirements that you or the team can think of. So you sit in a room and you start writing requirements. Well, I think it needs this and I think it needs that. Well, how do you know that you're done? How do you know that you fully characterize the design? How do you know that if you test against those requirements that the design is going to function as you expected it to? And this characterization of the functional model allows us to go through methodically through the design and write requirements against everything, at least one requirement against everything that requires an outflow. So we're going to have system requirements against each one of those functional chains. We're going to have at least one design requirement against each one of the individual functions. And once we do that, and we feel comfortable that each one of the functions is covered, in other words, that every one of the outflows of the functional chains and the functions has been covered with a requirement so we can characterize it and test it, we're done. And that's something that is very difficult for people to get to if you don't have this kind of functional diagramming built into your requirement methodology. Okay, so what's the value of all this? This is something I like to get back to. Have you ever had that gnawing feeling? And what I mean by that is, you know, when you have this idea of how your design works, what is it that it does? You don't necessarily, if you don't have a graphical representation and a set of functional chains that describe the capabilities and a set of functions that are components of that functional chain, you don't really have a formal understanding of how that thing works. And so when you're characterizing it with requirements, you're going to have gaps. And so if you really do a better job of this, I think you're going to have a much easier time sleeping at night feeling like your design is complete. What does this complete set of requirements really mean? I think it's really a characterization of every outflow of every function and functional chain. If the device fails, what exactly needs to be changed and what is the implication of that failure? This is a really important thing because we're never going to get designs perfectly right. But one of the things that's really nice is to come back to the design once we've identified a flaw and be able to put that flaw in the context of how the device or the design functions. If we do that, it's much easier for us to say, do we have a gap in the requirement set? Do we need to do new testing? And what is the implication of that failure across the whole system? Because now we've identified the functional chain and whether that function relates to more than one functional chain. And if it fails, the system fails. And what is the implication of the system failing is the lack of delivery of that capability. So it's a super important tool to saying, from an impact analysis standpoint, what could go wrong if we discover there's something in the design that needs to be fixed. So very important. I think this is a really important point. There's requirements are currently in most design are entirely subjective. It's just what do people need to put on the piece of paper to justify the fact that this design is going to work as we expected it to. In this case, I think we have a much better foundation to understanding, do we have all the requirements? Are they the right requirements? And how are they related to delivery of the capabilities we've said this thing is going to do? You know, is the plane going to fly? Will the wellhead on the bottom of the ocean, be able to shut off the oil flow? These things are really important to have a structured view of it so that if something does go wrong, we can quickly respond, we can understand what the system was designed to do, how it should function, and then we can respond quickly in the field. So if you need help integrating systems modeling with requirements, this is something we're expert at, and Fox Solution can really help you with that. So either with deployment of a system modeling system or with an understanding of the relationship between the systems modeling and these requirements, we'd be happy to help you, and please feel free to contact me. And again, here's my contact information. So thank you so much for sitting through this. I think this is one of the most exciting areas of design and really the bleeding edge of complex systems design, which is becoming more and more important as software has become sort of central to delivery of capabilities inside of these complex designs. So thanks again, and we'll talk to you soon.